Hi everyone, this is Miss Ward. Tonight you're going to be looking at Concept 4 of Newton's Laws unit, which is talking about Newton's third law. My son is again in the room, so if you hear little baby noises, you're just hearing my little son. Alright, tonight we're going to be talking about action-reaction pairs. And it's super important that you pay attention because there's a pretty common misconception with action-reaction pairs, which we'll talk about in a minute. And I want to make sure that you all do not fall into that trap of having that misconception. Okay, so Newton's third law describes the forces that objects exert on one another. All right? Nature never produces just one force at a time. It's impossible to only have one force. For example, you can't touch someone without being touched back in return. All right? If I pick up my son, if I'm holding Davy like I am now, obviously you can't see me, not only am I touching Davy, pushing on Davy, but he's pushing back on me. It's impossible for me to push on him without him pushing back. All right? As you stand on the ground, or sit on the ground, or sit in your chair, whatever, if you're sitting in a chair, you're pushing down on the chair is pushing back up on you. All right? So those are action-reaction pairs. For every action force acting on an object, there is a reaction force acting on a different object. The action and reaction forces are equal in magnitude but opposite in direction. This is commonly abbreviated to, for every action there is an equal and opposite reaction. Alright, now the abbreviation, I think, is where some of the misconceptions come in because it doesn't specify the fact that we're talking about different objects. That first definition, for every action force acting on an object, there is a reaction force acting on a different object, really sums it up and really says what this law is actually saying. Essentially, when you push on something, that thing is pushing back on you. All right, that's what this law is telling you. If I lean up against a wall, if I push against a wall, okay, push my back up against a wall, I'm pushing against the wall is pushing back up on me, and our magnitudes are equal to one another. All right? So, in essence, I'm holding the wall up, and the wall is holding me up. All right, so if you ever heard, people are like leaning against a wall and be like, oh, you're doing a good job holding that wall up. Well, you can tell them you actually are holding that wall up according to Newton's third law. All right, you're pushing on the wall is pushing back on you. The misconception, this slide really covers it, is that action-reaction forces always act on different objects. As a result, the two forces do not cancel each other out. So, a lot of times, people think that when you're talking about action-reaction pairs, you could be talking about, so if you're standing in the middle of a room and gravity is pushing down on you, normal force is pushing back up on you. People think that that is an action-reaction pair, and that is not an action-reaction pair because they're both forces acting on the same object. All right, those are two forces acting on you that have an end result of a net force equaling 0. All right? An action-reaction pair is you're standing in the middle of the room. The floor is pushing up on you. You're pushing down on the floor. All right? That's an action-reaction pair. You and the floor. You have to have two objects in order to have an action-reaction pair. Not one object and two forces. The important thing is to note as well is since they act on different objects, generally they're going to produce different accelerations because different objects have different masses. And since their force that they're pushing with is equal to one another, the force you're pushing down the floor and the force the floor is pushing back up on you are equal, your accelerations are going to be greatly different. All right? And that is super important. We're going to do a quick example that shows you that. So imagine you have two groups of canoeists, which didn't know until I read this problem that that's the plural of canoe, but okay. Two groups of canoeists meet in the middle of a lake. After a brief visit, a person in canoe 1 pushes on canoe 2 with a force of 46 newtons to separate the canoes. The mass of canoe 1 and its occupants is 150 kilograms, and the mass of canoe 2 and its occupants is 250 kilograms. What is the acceleration of each canoe? Okay, here in essence is what we have. We've got mass of 150 kilograms, mass of 250 kilograms. They push one another apart using a force of 46 newtons, which means you're going to have two forces. One pushing on the 150, one pushing on the 250, both being 46 newtons. All right? And they want you to know what the acceleration of each object is. We'll call this object 1, and we'll call this object 2 as they did in the problem. Alright, so looking at object 1, all we have to do is do our F equals ma equation. So the force was 46 newtons. And if we imagine this in an x and y axis, alright, the 46 newtons at the sorry, buddy. The 46 newtons is going to be in the positive direction that's acting on sorry, I had to calm the baby down. Sorry, the 46 newtons acting in the right, that's going to be dealing with the 250 kilogram object, alright, because that's the direction that that object would move. It would move to the right, and acceleration and force are always acting in the same direction. And then the 150 kilogram, that's going to be working. So let me color code these. I think that'd be easier. Let's change this to blue. So this one is representing the 150 kilogram object. Because you're not worried about which one is doing the pushing or pulling. You're worried about how it's the object it's acting on for this case. Okay, so 46, back to our problem, 46 newtons equals the, that's where this came from. So this should be a negative 46. In the object 1, it's in the negative direction on our x and y axis, which means that needs to be a negative 46. And that should make sense. These objects are moving in a different direction, so one should have a positive acceleration, one should have a negative acceleration. And if we define our x-axis like this, then the object on the left would have the negative acceleration, the object on the right would have the positive acceleration. They don't tell us the problem which one is on the left or the right, but if we draw it out and if we make that assumption, this is how it would work. So negative 46 equals 150 times our acceleration. Divide by 150. (46) divided by 150, and you end up with 0.306 meters per second squared. And for object 2, in your F equals ma, your force again is 46 meters. Your mass is 250. So your acceleration ends up being 0.184 meters per second squared. Alright, which means, if you look, that our object 2 is going to move much slower than our object 1. So if you saw this interaction, and the canoe 1 pushed against canoe 2, canoe 1 would probably move much further away, or looks like it would move much further away than canoe 2, because it's lighter. It's easier to be moved, right? It has less inertia. The massive object is more likely to resist motion, going back all the way to Newton's first law, so it has more inertia, all right? And using our F equals ma in our second law, we see that this is how we figure out their acceleration, and these are action-reaction pairs. So it all ties in together, all right? All right, now, last thing before we finish up this concept, there are limits to Newton's laws. We apply Newton's laws to everyday objects, so objects on a larger scale. They describe the mechanics and are generally called the law of mechanics because of this. For microscopic things such as atoms or not cells, but atoms or molecules, quantum mechanics is actually used to explain the motion. So it doesn't apply on things on an atomic level. All right, it only applies to things on what we call the macroscopic. So opposite microscopic, means small. Macro means large. So macroscopic objects, large objects, are where we can apply Newton's laws to. So that is the limit for these. Quantum mechanics we don't get to in high school. You would learn about it if you took it on a collegiate level. All right, make sure you go on, you do your whisks. If you have any questions, please let me know. We will talk about them tomorrow in class. Have a great night.